Okay, can you see it? Is it okay?
Yes.
Okay, perfect. So hello, my name is Valentin Guillet, and I'm going to present the article titled Neural Distillation as a State Representation Bottleneck in Reinforcement Learning. This work was conducted at ISAE Superior, which is part of the University of Toulouse, in collaboration with the Agence Innovation Défense in France. So first of all, what is distillation? Distillation is a simple method introduced by Hinton et al. In 2015 that aims at training a neural network to imitate the output of another given neural network by supervised learning. The network to imitate is usually called the teacher or the expert, as we want to copy its abilities, and the learning network is called the student. The optimization process is very straightforward, as the student is trained using cross-entropy loss between its outputs and the expert outputs. In the case of reinforcement learning, this output generally corresponds to a policy or a value function. The distillation process can be easily extended to a multitask setting just by regularizing the student network towards more than one expert at the same time. The student network is generally chosen with the same architecture as the expert networks. So in this setting, the distillation must also act as a network compression process. One way to achieve information compression is to extract common features that are useful in several tasks. Since sharing knowledge takes less space than learning distinct skills, thus we hypothesize that distillation can act as an information bottleneck when used for multitask learning. Specifically, we claim that the features extracted by the student network are useful for many of the tasks to solve, which corresponds to learning useful state representations, which in turn allow for skills transfer between tasks. So in order to verify this claim, we define three criteria that measure properties that we find important for a good state representation. First, the ability to select important variables. The final policy should depend strongly on important variables and filter out confounding, uninformative, redundant, or noisy inputs. Then, state separability. The encoding should cluster together states sharing the same optimal action to avoid overfitting and thus ease generalization across states. Lastly, robustness. Application of the final policy to new tasks should preserve a certain amount of performance. So first, we apply these three criteria to a toy environment we developed based on the standard pendulum environment from the OpenAI agent suite. In the original environment, the goal of the agent is to balance a pole upward by applying a torque on the pole, given its angle theta in the form of cos theta and sin theta, and its angular velocity theta dot. We modify this environment by defining a few levels in which the input is extended to be of dimension 30. For each level, the new state contains the original three state variables plus some other variables. First, a set of 10 random linear combinations of these variables with different weights for each level. This creates information redundancy, but which does not permit generalization between levels, as linear combinations are different for each one. Then we add a set of 10 fixed noisy linear combinations of these same variables, but shared between levels this time. This creates information redundancy that permits generalization between levels, but which also includes measurement noise. We then add a copy of 3 random variables among the 23 previous ones, redrawn for each level. And finally, we add a set of 4 central Gaussian noise variables. We then trained experts on a set of 12 of these levels before distilling these experts in a single student. To evaluate the ability of the student to filter out variables that do not lead to generalization, we evaluate each feature of importance for the experts and the student independently. For this, we compute the gradient of the network's outputs with respect to the state variables and report the amplitude of these gradients. For each level, the first line corresponds to the experts and the second line corresponds to the student. You can see the 12 levels there. We can see that the experts base their policy mainly on the first 13 variables, as they contain enough information to solve the task. The noisy variables and the copied variables are only slightly important. It's these ones. while the Gaussian noise variables are plainly ignored in the last four ones. However, the student only focuses on the first three original variables because they are the only ones that can be used for all levels and without any noise. This experiment shows that contrary to the expert, the student is able to focus on common features between all levels while ignoring redundant and noisy variables. Moreover, when we vary the number of levels used for the distillation process, it clearly appears that the higher number of levels used, the better the filtering process. This shows that variability on the training levels is directly linked to the ability to extract general features. Measuring state separability is a harder task, since the extracted features live in a 32-dimensional space, because of our architecture we use for our networks. To be able to visually represent the space, we used two standard dimensionality reduction methods, namely Disney algorithm and partial least squares regression, PLS, that capture correlations respectively between the state encodings and between the features and the network outputs. To avoid any human bias when judging the separability on these figures, as you can see, it's pretty difficult to say by just with our eyes, we trained a linear SVM to predict the action given by the network from its features, both in the 2D projection space and the original 32-dimensional space. The scores of the SVM are reported in this table. The results clearly show that in each case, the student network extracts features that are more separable than the experts, and even more so when the number of levels used for the distillation process is high. There is a bigger gap here. This confirms that distillation is efficient to separate states according to their corresponding optimal actions, which mitigates overfitting and easy generalization. Finally, in order to measure the robustness of the student policy, we evaluate it on a set of 100 new levels not seen during training. As a student mainly focuses on features that are shared across levels to take its decisions, we expect it to be able to solve these levels even without retraining. The histograms here report the score of different agents, depending once again on the number of levels used for distillation. And it appears clearly that when the number of levels used is high enough, distill networks are able to solve answer levels as well as an expert which would have been trained on this specific level. By contrast, an expert evaluated on level different than its level of expertise exhibits the same performance as a random agent, basically. This experiment shows that the robustness criteria is also verified for the distill agent. So we were able to show on our controlled environment that distillation is an efficient method to learn a useful state representation with our criteria. However, our synthetic environment is quite simple and easy to solve. Therefore, the next step is to extend our analysis in more complex settings. To confirm our findings, we follow the same experimental protocol on two visual benchmarks, Atari games and projection games. In the Atari benchmark, each game is very different and only visual features, such as shape detection models, for example, should be transferable. In the projection benchmark, however, every game is divided into levels with different layouts, but sharing the same dynamics. Therefore, this benchmark appears closer to the control environment. We slightly modify our algorithm to adapt to these benchmarks by following the protocol proposed in 2016 by Parisato et al. In their actor mimic networks article. The idea is simply to add a regression term in the student class between its features and the expert features, as it seems to improve the efficiency of the distillation phase. First of all, it's useful to check that the student network is able to reach the same performance as the experts. We report the scores of the experts and the students in each case for each game, in the Atari case and in the function case, but I won't spend too many times here. Because of the visual inputs, it's more difficult to evaluate the ability of the student to only select useful variables. As for the control environment, we use salience maps to measure the gradient amplitude for each pixel of the input image. However, these salience maps are hard to interpret because the pixels a human would consider as important change all the time as the game progresses. For instance, in the coin run game, an enemy is important, but the enemy is moving across the level. So the important pixels change at each time step. So instead, we can evaluate the number of these pixels that strongly condition the network's outputs as if the network makes decisions based on the background, this number will be large, whereas it will be lower in the case where the agent focuses its attention on a single object, such as an enemy, as we said before. We thus report the number of pixels with intensity in the saliency map is greater than a threshold for both the experts and the student. This number should act as a proxy of the number of important variables in the input image. For each environment, we observe that this number is lower for the student network, which shows that it's able to focus its attention on smaller parts of the image once again. To evaluate the state separability, we will use the same protocol as for the pendulum environment. We use the t-SNE algorithm and PLS regressions to project features into a smaller space, and then train a linear SVM to separate features based on the corresponding action given by the network. Once again, these results show that for every game, the state representation space learned by the student is better suited to separate states. So once again, it avoids overfitting. Finally, we evaluate the robustness of the distill policy and the projection benchmark. We do not consider the Atari benchmark here, as the Atari games are too different from one another to really transfer a policy without any retraining between games. However, we can see for a coin run game, what's interesting is that the simple policy, which consists in running to the right and jumping as often as possible, is able to reach a decent score, as it's often enough to avoid all enemies and reach the coin at the end of the level. We can observe this phenomenon on the coin run graph, which shows that the distill agent was able to learn this general policy and solve half of the evaluation levels without any retraining. In the other half, we found that the failing reason was often an enemy on the road that the agent did not take into account. And we talk a bit more about a jumper and big fish in our paper. In consequence, robustness seems to be harder to reach in the general case, but if there exists a good policy common to several levels, as in the case of coin run, then the distillation process is able to learn it. In conclusion, it appears that distillation used in a multitask context acts as an information bottleneck that mitigates overfitting and allows to learn useful state representations. More specifically, the distillation process trains policies that are able to filter out task-specific features, thus allowing them to focus on variables in the observation space that are relevant for multiple environments. By encouraging generalization and transfer between tasks, distillations could thus be a useful tool to tackle lifelong learning. And if you want more details about our work, don't hesitate to read the paper. Thank you.
Are there any questions? Maybe I can ask a very generic question. So you've explored this mechanism within RL. I would assume that it would work equally well in other domains as well as supervised learning and stuff like that. Have you considered that, or yeah?
No, we did not look at that. We are mainly focused on reinforcement learning because of the difficulty of the tasks, and we had lifelong learning in mind for to apply after. But I would say that it should also work in the supervised learning context too.
If there are no other questions, let's thank the speaker again.
Okay.